Before we continue, I'd like to use Mandarin to quickly review what we have taught in the last hour. Okay, so make sure students get a point. 我们刚刚在讲这个 convolution 这件事情，我们有用两个不同的观点在描述 convolution layer， 对不对？第一个观点是先不要管任何事情，我们就看图。那也就是说，不同的 neuron 它考虑的是不同的 local information。H1 指的是1267 hidden neuron 2指的是2378。好，那这件事情其实非常 straightforward， 就是考虑不同的 local information。但是这是第一种解释的观点，然后weight是一样，还记得weight是一样哈。第二个解释的观点就是我们刚刚讲的这种比较图像化的解释观点。好，我们把资料先不管是一维还是二维都可以解释哈。那但是二维比较看起来比较 fancy， 我们就用二维来解释哈。那也就是说，我们有个 weight 绿色的1234W， 好，那我们用走的方式从左上角一格一格的走，往右走，然后走完之后往下走还是这样 padding。走的时候你要注意看哦，因为我们的算法是做乘积嘛哈。乘积有一件非常不是乘积就是 product， 就是 pairwise 的这个乘积哈。那这个乘积会有一个效果，这个效果会有一个物理的解释所以我们刚刚讲就是说，假设是1264跟 W 要相乘W 乘1嘛W 2乘2嘛W 3乘6嘛W 3乘4，相乘就假设X 是黑白的影像。所以它的值就只能是0跟1了。我们是假设 input data 是这样，那实际上可以不是可以是任何数据都没有问题。那 W 呢是 weight， 对不对？我们假设把 weight 的值域限定在0跟1之间那当然也可以是正1到负1之间这个也没有关系。我们现在在做这个 kernel 这个 work 的时候遇到这个是 W 乘 X1 2乘2 3乘6 4乘7的时候，你会发现如果这个的乘积的值的和就是所谓的 product sum product sum 的值如果是很大的话，那就基本表示 W1 应该要跟 X1 相乘是正的，而且是大的值。2跟 X2 W2 跟 X2 相乘要是正的，然后是大的值。W3 跟6相乘要是正的是大的值，4跟7相乘要是正的是大的值，它的 product sum 加起来才会是大的。那如果 X 的值域只有0跟1，然后 W 的值域呢，我们把它限定在 0.0 到 1.0 之间的小数的话，那也就是说，怎么样的值乘起来最大呢？就是它们两个一模一样嘛，对不对？我们右边的那个例子是说，如果 X 的是0101那 W 刚好也是0101绿色的，它们乘起来是2嘛，它上面还是2嘛，这个值其实已经是这里面最大的，不可能有更大的，对不对？可是你要想如果这个0101它乘上的是红色的，好不好？对不对？0.0、1.0、0.0跟0.5我们右边不是有一个0.5吗？乘的话，你会发现左边的00是一样的，右上角的1是一样的，可是右下角的1X7 嘛，它是黑色的1嘛，对不对？可是 weight 的4是红色的0.5的话，它们乘起来只有0.5，对不对？所以它的和它上的和是只剩下 1.5， 就没有2来的这么大了，对不对？然后你甚至可以是完全相反的就是像我们刚刚讲这个紫色的例子0101乘上1010，它乘起来和是紫色只有0.5，也就是说呢，这个 product sum 越大，它实际上它的物理意义就是眼睛你可以看到这个物理意义，就是 W 的这4个方块跟 X 现在 focus 在1267嘛，这4个方块越像，它的 product sum 的和就越大，好吗？所以它的物理意义是我们想要找这个 kernel 的样子，这个 kernel 样子才知道嘛，就是0101嘛，在这整个 image 里面就是 X1 到 X30嘛，我们不是这样依序的走过吗？这个 pattern 就是这个花样，这个花样就是0101嘛，绿色的0101，这个 W0101的这个花样到底在这整个 image 里面出现在哪里，对吗？因为你这样 work 这样走嘛，对不对？你 work 乘积出来的值如果是大的，表示说这里有一个跟这个 W 很像的这个 pattern 出现在原本这个 X 的某个 local 的地方。那如果这个继续走到某个地方，乘积出来是很逼近0的，就很靠近0的，比方说 W 这个 pattern 0101是没有出现在这里，所以它的物理意义就是我们要想办法找到在这个整个图里面，所以才要走， 我们刚刚有讲英文，刚刚讲过，就是说实际上我们不知道这个 pattern 在哪里，所以我们才要用不同的 neuron 去走它。走完之后，你就会发现，你原本是一个5×6的 x30嘛 ，x1 到 x3的值嘛。那如果有 padding 之后，你这样走完之后还是5×6的 output， 而这 output 的这个我们姑且称之它为 map， 好，这 output 的 map 呢，最小的值是0，最大的值是2，所以你就看看这个图里面有多少2出现，或是很靠近2的值出现，表示你要找的那个 w 的样貌0101有出现在这个原始的 x 的这个图的某个 position， 会在这个 map 里面，如果越这个 output 的 map 有越高出现2的，它就是在那边出现。那当然这个例子是一个2×2的 kernel， 你的 kernel 可以大一点啊，比如说3×3啊，6×6啊，你可以6×6的话，那你就36个格子，对不对？你可以设计非常多不同的花样，也就是所谓这个 weight 的花样。这 weight 的花样可以非常特别，可以是一直线，可以是一个横线，可以是斜线，可以是一个弧线 ，whatever， 对不对？你看哦。如果这个 weight 是0101的话，它就长得像那个黑白的格子，对不对？对吧？那你可不可以是3个直线、3个横线、一个圆弧的一部分、一个 curve、一个什么、一个复杂的图？可以。你的 kernel 里面的值可以长得任何的样子，而那个任何的样子，你 visualize 来看的话，就当做黑阶的就是黑白的 image 来看，它会有个样子，而这个样子会 go through 整个原始的 x 的图去找这个 pattern。这个 weight 的这个 pattern 在原始的图里面哪里出现过？好，讲完了，这个就是第二种比较直观的解释，就是用 visualize 的方式解释。那我们在做什么？我们在找那个 pattern 出现在哪里？那我们为什么要找这个 pattern 出现在哪里？你可以想啊，如果这个 x 的值啊是个 image 的话，那我就会在找啊，如果那个 pattern 描述的是一个圆弧的线段，好，那我就在找啊，这个图里面到底哪个 position 有圆弧的线段，如果它被 match 了，那个 output 的值一定超大的，对不对？好，那你要想哦，这个不是只有2D 可以用啊，如果在一个1D 的 series，我们前面不是讲过 series 嘛，对不对？如果在一个1D 的 series 里面，然后所以我的 kernel 也会是1D 的，对不对？好，假设我们现在在找这个1D 的资料，像是股票的资料好了，对吧？所以里面就放股票的值嘛，好，100、150、200，那就是上涨，对不对？啊，200再下跌就是180、170、160、150。那如果你设计一个 kernel， 好，它就那个 kernel 比较短了，对不对？比如说一个 kernel 只有4个连续的 sequence， 或是5个连续的 sequence， 里面就放值，放什么值呢？你就放100、200、300、400。那这个 kernel 的值一样会 go through 整个 time series， 对不对？那它在找什么？它在找这整个 time series 里面哪里有从100找到400这件事情。如果有的话，它的 output 值就会大嘛，对不对？它 output 值大，我们就知道那个 kernel 的内容，比如说那 kernel 100、200、300、400，我们就知道哦哪里有原始的 time series 里面超长，比如说1000个事件的 series， 然后你就拿你的 kernel 这样滑过去，从1到4，然后再2到5嘛，3到6、4到7，这样滑过去就到最后一个，你就可以知道哪里出现过100、200、300、400这样子的一个 pattern。所以不管是1D 的还是2D 的 convolution layer 都在找东西，找什么东西？找那个 weight 里面的那个样子。好，这个是中文的解释。好 ，OK， let's continue. We know convolution layer is trying to find where is the pattern of the kernel in the original data set. Okay. However, how many kernels could we have? Actually, we could have many different kernels. Theoretically, it should be multiple kernels. Okay, so theoretically it should be like this. So basically we can view it as this way. Okay, we have part of the hidden neurons, H1, H2, H3. For example, we have 3 neurons like this. Okay, this neuron, they only take, for example, partial information. Okay, they have a weight right here and light green. Okay, the second weight, the second neuron. Okay, but they have the same weight, so I use exactly the same color, something like that. And the other green one, like this one, something like that. For this kernel, okay, so we said the green is kernel number 1. This kernel has several different neurons. They share same weight, but they focus on different local information. So that's kernel number 1. But actually, when we use convolution neural network, usually we will set up several different kernels. So that is the red one. Okay. Okay, we have kernel number 2. Kernel number 2, maybe the shape is a little bit different. For example, the red one has 3 kernel as well. It has red weight. Okay, the other one, they focus on different information, something like that. They share the same weight for this second kernel, and so on and so forth. So 2 different kernels. Okay, so we have 2 different weights: the green ones, a green one, and the red ones. For each kernel, okay, they will walk through the original data, focus on different local information to gather the information to see if the patterns of the green weights can be activated in certain place, in certain position of the original data, right? And of course, I can deploy. I can use another kernel, which is the red one. It has different weights, and it also works through the original dataset x1 to xn, for example. And it has 3 neurons. Each one focuses on different local area, and so on and so forth. So basically, we can do it many times. So you can set up many different kernels, multiple kernels in a layer. Of course, you can set this value when you use TensorFlow, PyTorch, Keras. Those packages, they will ask you how many different kernels you would like to use in a single convolution layer. And for each kernels, what is the size of this kernel? For example, 2x2, 4x4, 6x6. And also, again, how did you want to walk through the original data? And you want to do padding or not? Okay, so you have to design your own convolution layer. Okay, there are several different parameters. So usually we have several different kernels. Okay, that is the first things. Okay, the next one is usually after we have those convolution layers, we will append another specific layer after the convolution layer, which is called pooling layer. And usually we use max pooling after a convolution layer. Okay, usually we put another layer called pooling layer. What exactly pooling layer means? Okay, let's take for example, let's say P1, P2. We have 2 additional neurons in the pooling layer. Okay, of course it received the information from the previous layer. For example, P1 received the information from H1, and of course you can design an activation function with something right here. Okay, it received the information from H2, and for P2, okay, it received the information from H2 and H3. Okay, now it looks like a convolution, right? Because P1 and P2 only consider local information. That's right. But however, the mathematics right here is not product sum. It's not like the convolution layer. Convolution layer has a weight, right? You have to product it with x, right? And to make a summation and send it into the neuron, right? But the max pooling layer is, okay, you can take a look at this name, max. That means this layer does not do something like product sum. They choose, for example, the P1 receive 2 information from H1 and H2, right? P1 select the largest value received from the previous layer, previous neuron, which is H1 and H2. Right here is try to output the value of H1, the max value of H1 and H2. The next one is the max value of X2 and X3. So basically the computation is a little different. It is not product sum. Max pooling layer means I would like to focus on local information as well, which is only H1 and H2 or H2 and H3. However, I don't do product sum. Okay, max pooling layer. Okay, since the name is max pooling, it tries to shrink the size of the convolution layer. Only select important information and pass the important information, which is the higher value, to the next layer. Okay, of course, there should be some other layers behind the convolution layer. That is very simple. Just simply select the largest one. So usually, okay, in the previous one, after we do convolution, okay, it is a 5 by 6 original x1 to x30. image, right? After convolution, of course, after padding and convolution, okay, we have another output map, which is also 5 by 6. But the value inside this 5 by 6 output map, it specifies where the weight, the pattern of the weight, right? Because the larger the value is, the more similar you can find. There is a pattern which is very, very similar to the weight pattern. So after that, we do pooling. So in a small area, I only select the largest one as the representation. Then here is the neuron P1, which can be activated. For example, H1, okay, which only consider X1, X2, and X3, right? So if H1 is activated with this weight, which means I can find a pattern in X1, 2, 3, which is very similar to the green W. So it activates. And maybe for H3, it considers some other X. However, H3 is quite low, which means I cannot find the green pattern, green weight in X4 and some other place. So maybe for H2, so this another one, H2 only consider partial information X2, X3, and X4. Maybe the value at H2 is not as high as H1, so it is maybe just some smaller number than H1. P1, it considers two information from H1 and H2, select the highest one. Because H1 has been activated, of course, we can have a lot of different pooling layer neurons right here. So originally, maybe X looks like this, okay? X1, X2, X3, X4, X5, 6, okay? So the first neuron, okay, maybe it focuses on this part, okay? The second neuron, the purple one, maybe they focus on this one. So it comes up another map, says here with a very high value. So X1, 2, 4, 5, it matches the weight. The next part, the purple one right here, it says, okay, X2, X3, X5, X6, they not very similar to W, but somehow it has certain value right here. So that is convolution. So maybe that is something very small. Means this W pattern does not exist in this local area. So when we do pooling, it's convolution. So next thing is pooling. Pooling still output certain value. However, for example, it considers the first two results from the convolution layer. As we mentioned, it only select the largest one. So here, that is P1, right? P1, that is P2. For P1, okay, it select the largest one, okay, the largest one, which is right here. And for P2 and other local information after we do convolution. So maybe the value is 1.0, that's 0.5, that's 0.0. So it always select the largest one. So after we do the convolution, after we do the max pooling, there's another map. Okay, after max pooling, it specifies where your images has such kind of kernel pattern, so that we ignore the small value after the convolution layer. We only select the larger value in the convolution layer. So we ignore the smaller ones. So basically, the size of the convolution layer. In this example, we select value out of 2, right? Because we have right here we have 2 lines right here. So we select the largest value out of 2 values of convolution layer, right? So basically, the size after max pooling, okay, the size will decrease. So and so on and so forth. So here's the map after pooling. Okay, it specifies where the patterns exist. So that's quite simple. So in this case, we can filter out. Filter out 是滤除哈. We can filter out some meaningless, some useless information from this map. We only preserve important information in the output of pooling layer. And of course, for some other application, you can select, for example, you can select the minimum value from the previous layer. You can calculate the average value among the value of convolution layer. Okay, but usually we select the maximum value from the previous layer to construct your pooling layer. So as I mentioned before, since in the convolution layer you find the largest value, right? That is because your pattern x1, 2, 6, 7 is very similar to your weight 1, 2, 3, 4. So you output a large value. So in the pooling layer, you select the larger one, so you can discard all the other values which is smaller. So that's how did you find a pattern and filter information by using convolution layer and pooling layer. So usually we have the x value right here, and usually we do, for example, we do convolution and we do pooling, and then we do another convolution and we do another pooling. You can design your own neural network, okay, by stacking different types of layers. But usually you can do convolution first and you can do pooling first. So it creates a convolution. We can say it is a module. Okay, you can stack different layers. And for example, if I have two sets of convolution and pooling, and at the last I can do, for example, softmax, right? And then we can output our Y. That is a very simplest convolution layer. And at the end, we sum up all of the information extracted from the convolution layers and pooling layers. And we do some softmax to consider all the information extracted from the previous layer. And we output what we want to output, which is Y. So that is convolution and pooling. And in practical, you can stack 3 or 4 different set of convolution. The kernel size used here, and the kernel size used here, and the number of kernels in these two different convolution layers. You can set different numbers. You can simply just Google convolution neural network, MNIST, which is one of the famous data sets. So you can see that you can always find all those very beautiful, very well described information right here. For example, let's take a look at this one. You can always find there are several different structures invented or designed by different data scientists. Okay, they are trying to apply different layers. So here is an example of very classic convolution neural network. As you can see, it has 2 sets of pooling, and so that is convolution plus pooling, convolution plus pooling. And here is a V4 neural network, or if we use this word dense, okay, if you have tried Keras or TensorFlow, that is just a dense. And at the end, okay, here is a softmax. And here's the original X, here's softmax as Y right here. So you can see that the original data set has x1, x2 to x, okay? So here, for example, our input is an image, okay? It has 28 by 28 pixels. So basically you have 784 pixels. So you can list them as x1 to x784 in this classic design, okay? The kernel size is 3 by 3. So basically you have a kernel size like this. And your image is 28 by 28. So you will go through the entire images. Padding is 1, means yes. It means I would like to do padding. So the stride here is every time I do kernel walking, take one more step to the right hand side, to the end of the row, okay? To the next row. Again, one step to the bottom. So you can simply just scan this 28 by 28 images by using this simple 3 by 3 kernel. Since you do the padding, so the result is still 28 by 28 because you do padding. So you can keep the image size still the same, 28 by 28. Important value is right here, 32. That means we have 32 different kernels. As I mentioned before, we can have multiple kernels right here, right? So it designed 32 different kernels, and each kernel, its size is 3 by 3. We have paddings, and our stride is 1. So after we do such kind of convolution, okay, we have 32 different maps, 32 different results from 32 different kernels. And for each kernel, for each kernel we have weights, right? For each kernel, we have a 3 by 3 weight. So that is the result. And of course, the data seems like bigger, right? But originally we have 28 by 28 pixels, but now we have 32 different kernels. For each kernels, okay, we have 28 by 28 output result right here. Okay, so next we do pooling. The pooling is max pooling, right? The kernel size is 2 by 2, which means in a very small area, which is 2 by 2, I only select one largest value among these 4 values. I will put this value in somewhere here. And this 2 by 2 pooling kernel still go through all the 28 by 28 result. And the stride is 2, which means every time when I shift my pooling area, I think since the kernel size is 2 by 2, I didn't do overlapping. Every time I move, I shift 2 blocks. If the original size like this, okay, the first time when you do the pooling, okay, you select the 2 by 2, right? The next time you do pooling, the stride is 2. So next time you do pooling on this 4 value, because you shift from here to here, you walk 2 pixels. So basically, the output is from 28 by 28 to 14 by 14, because your kernel size is 2 by 2. Every time you move your kernel, the stride is 2. So basically, your size shrink from 28 by 28 to 14 by 14. And still, you have 32 different results, because you have 32 different kernels when you do convolution. So the size is 32 and 40 by 14. So that is the first set of convolution, including 1 convolution and 1 pooling. Again, you do convolution again. The output, the input value is the output of the pooling, the first pooling. So this time, we still have a kernel which is 3 by 3. We still do pooling and the stride. You walk, okay, the shift is 1 pixel. So how many? 42. Okay, since you do padding, since you do the stride 1 to 1, so the size is still 14 by 14, right? Because you do padding. Okay, but now originally we have 32 different output, because at the first beginning we have 32 kernels. Each kernel's output 1, we say pieces. Okay, 1 pieces of data. Okay, and for each pieces it is 28 by 28, and then after pooling is 40 by 40. But now we set, okay, how many kernels we like to use for this second convolution layer. We set it to 64. So now, using the original 32 pieces of data, we create another 46 pieces of data by using the original data right here. So that is 64. So after the second convolution, we do the second pooling, which right here we have kernel 2 by 2, stride is 2 by 2, so the size shrink. So after that, we have 64 pieces of data. Each data has 7 by 7. So after that, in total, we have how many data right here? 64 times 7 times 7. So we have a lot of data right here. And at the end, is this number? Okay, we have a dense layer. As we mentioned before, we can set how many neurons in a dense layer. Okay, we gradually, I don't know how many layers, maybe 3 layers right here. Okay, we gradually decrease the size of dense layer from 3,136, which is from here. The next layer has only 128 neurons in this dense layer. And at the end, it's right here, we have only 10 values, 10 neurons, which can receive all the information passed from the very first beginning. We have 28 by 28 images. we go through convolution. So we have 32 different point of view, 32 different kernels, which can scan the 28 by 28 data. Okay, from the previous input data, we have 32 different point of view, 32 different weights to find different patterns. And then we do first pooling layer, trying to aggregate all the information to select only the highest value from the previous convolution. And then in the second convolution, we find another 64 different patterns, whether I can find another pattern after we do the pooling. And then we do the pooling again. And then we have 3,136 different point of view, different information received or extracted from the images. And we do a dance to discretize to 128. And then we do a softmax with 10 neurons. So what is the application actually it is? It is a classification problem. Okay, so at the right hand side we can see that 0, 1 to 9. It is a classification of digital handwriting numbers. So at the left hand side we can see that it's 4. We can see that in our course website, okay, I provide several different things right here. For example, you can see that the data set MNIST, okay, you can simply just click it and it brings you to the Kaggle. This specific application, okay, they try to do a classifier. Okay, so we have a very nice description right here. We have several different pictures. Each picture is 28 pixel by 28 pixel. This picture looks like this, so you can simply just Google MNIST. The input data is like that. So for each digit right here, it is a 28 by 28 pixel. This 700 and 700 features, okay, they are real numbers. If the pixel is black, and it will be close to 1 over 0. So you use 28 by 28 features to describe these images. These images are all handwriting digits. So we are trying to make a classification to distinguish 0, 1, 2, 3, 4, 5, 2, 9, which one of them. So we have to make a classifier. When we do such kind of classification, we need some information. What information has been included in the original message, original input. So right here, the first two convolution layers, they are trying to extract what kind of patterns has been included in the original images. The kernels right here, there are 32 kernels, right? Those kernels right here, they are trying to identify some local information. What kind of information they are trying to specify? Okay, this is a 3 by 3 kernel, right? So maybe one of the kernel, okay, 3 by 3, they are trying to figure out if there is a straight line in this 3 by 3 kernel, or there is another kernel which may look like this. They are trying to figure out if there's any local pixels. They arrange like this. It's a line, diagonal line. Why the first convolution they are trying to find those patterns? Because they believe those patterns are valuable information to help the classifier to specify it is 0 or it is 1. Because when we take a look at some digit like here, for example, maybe one of the kernel, they are trying to figure out if there is a curve like this. Because when you describe some local information, okay, maybe this curve is part of 9 right here, okay, or part of zeros. They are trying to find local pixels. They have specific curves or specific patterns, which is part of the pattern of a digit, right? If there is a pattern, okay, they are trying to figure out something like that. This pattern might be right here, might be right here, 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 or here. So the first convolution, they are trying to find if there is any partial local area patterns which can be matched by this kernel, and they will trigger, as I mentioned before, they will output a larger number. A larger number will be selected by the second layer, which is a pooling layer. So the pooling layer can pick where the specific pattern happens in the original image. and they pass through the information to the next convolution layer. The convolution layer can still find if there's any local patterns can be identified by this convolution layer and picked by the polling layer. So all those information, all those kernels, they are trying to find the specific patterns, and this pattern will be activated in all the following neurons. So according to the information we collect by the convolution layer and polling layer, all those information will be gathered right here, and among them we will try to build a classifier to make a decision right here, which is a softmax. We collect information, we weight those information. Of course, there are some weights right here, right? We weight those information, we come up at final solution. Okay, this is number 4. So number 4, this neuron will be triggered by the weight here. We can see that is evident. And here, the classifier right here is how do we weight those evidence. And right here is extract pattern from the original data, which is the image. So that is the explanation of convolutional neural network. So of course, there are some other informations you can obtain from our course. For example, there are a lot of examples which is use the NIST, which is the digital number classification. Okay, and how do they use convolutional neural network? Okay, here is the official example provided by Google, TensorFlow. How do you use TensorFlow to construct a convolutional neural network and try to identify? In this example, they are trying to identify different animals, because different animals has different characteristics. So weights can help them to provide different point of view provided by Google, and here is example provided by Google as well. Okay, tell you how to classify. So the code is right here, so you can take a look at this code.